Hello, my name is Pubali Datta and today I am going to present our paper on workflow-aware access management in serverless platforms. Let's start with an introduction of serverless computing. Serverless computing is a new cloud computing paradigm that has become popular in the last few years. The serverless platforms free the application developers from all backend hardware and software stack management tasks. It takes care of load balancing and auto-scaling, allowing your application to scale up or scale down to zero according to the request load. The users pay only for the duration their application executes in the cloud, thus bringing down the cost significantly. It also enables rapid prototyping of applications using third-party functions available from public function stores. All these exciting features rapidly gained popularity among the industry practitioners, and we have seen a lot of big players crowding the space in recent years. The serverless programming model, it differs from the traditional web application development in some ways. The serverless applications are comprised of small functions that execute for few cycles. Application logic is expressed as a set of workflows, where each workflow is essentially a set of functions and other serverless components like data stores and event queues who communicate with each other to achieve some goal. Each function execution is stateless and isolated. That is, a function instance, usually a container, is spinned up whenever a function execution request comes into the platform. Now we will delve deeper with an example of a serverless retail website where users can browse through different products. The purchase product function is launched when a user clicks on a product to buy it, and this function launches the authorized credit card function that requires a credit card database according to the supplied parameters. After successful or failed authorization, the purchase status is sent back to the website portal. All of these functions are protected by role-based access control policies, which are popularly called Identity and Access Management Policies or IAM policies. In serverless, to achieve high performance in the face of high request load, in addition to scaling up the function containers, the platforms also cache these containers in memory and recycle them to avoid the costly teardown and respawning operations. Let's make the serverless retail application a bit more complicated by introducing another workflow. We have a product catalog database which is accessed while users browse the website and purchase products to fetch product information. There are inventory managers who populate the catalog by writing to the database using the create product function. Because the serverless functions exist for only few milliseconds and apparently they are stateless, isolated, and well protected by IAM policies, it seems that this is a perfectly secure retail web application. There is no way these short-lived functions can provide an attacker a foothold, resulting in a massive security breach. Unfortunately, researchers quickly discovered that this is not the case. For example, an hacker got their hand onto some leaked credentials of an inventory manager and was able to find the bug in the authorized credit card function that enables them to relay commands and pass bad arguments that causes them to retrieve an SQL dump of the database. We might wonder how the attacker can pull off this time-consuming operation within the short-lived authorized credit card function. Recall that the reusing of cached containers in the serverless cloud keeps the container alive long enough for the attacker to get their prize if requests keep coming in frequently enough. In spite of the strong RBAC policies in place, the stolen data can be laundered through the downstream functions like send purchase status, which can publish the stolen data to the website, or can leak the data through legitimate platform APIs like email, phone, or message that it might have access to for its operations. The point to be noted here is that the attack is possible because of flow violation. The product creation workflow has nothing to do with the product purchasing workflow. The inventory managers should never be able to invoke authorized credit card from a completely disjointed workflow within the application. Unfortunately, since traditional IAM authorizes each function in isolation, it is not clear to the platform that an information flow has been violated in our attack scenario. Thus, traditional IAM policies are inadequate to prevent sophisticated attacks, and this is what leads us to the key idea. The key idea here is that the attack explained before is the result of a mismatch of abstractions. Application developers express program logic in the form of inter-function workflows, yet authorization is performed only within the context of individual function transitions. As a solution, we designed Will.IAM, an access control framework for serverless cloud. Rather than assigning static permissions to functions, Will.IAM performs proactive and workflow-sensitive access control. In Will.IAM, we define two additional data structures for an application. The first one is a protection state graph. The protection state graph depicts a conceptual architecture of the serverless application in form of workflows along with the database permissions required by a function in order to execute. We can see here three different workflows. The workflow with ingress point create product needs both read and write permission to the product catalog. The browse product workflow needs read permission to read product catalog. However, the browse product function sometimes may invoke purchase product, which initiates a new workflow that would require read access to the credit card database. The invocation of purchase product from browse product is conditional and it might not occur all the time. The labeling state graph describes the different roles assigned to the users of the serverless application and the permissions possessed by them. Roles can be hierarchical such that the parent roles encompass all permissions of their children. In our example, the public role has the least privilege and only has permission to read the product catalog, while the customer role is permitted to read both the credit card database and the product catalog. Similarly, the inventory manager is only allowed to read from and write to the product catalog database. The admin role possesses all permissions, which is expressed by positioning admin as the parent of both the customer and inventory manager roles. Now we will discuss how Will.IAM achieves workflow-sensitive proactive authorization after we have defined the policy graphs for the application. An application user sends an invocation request to function foo, which hits the API gateway of the cloud platform. Will.IAM extends the API gateway to specially handle requests originating from outside the application. The authentication information within the request header is sent to an authentication server to assign a role to the request. Next, the request along with the role is sent to the policy evaluation service of Will.IAM. The external requests are examined by the mandatory policy evaluation routine. The labeling state graph is queried to fetch the permissions associated with role R, and the protection state graph is consulted to compute the set of permissions required to completely execute the workflow beginning at foo. If R's granted permissions do not contain all the required foo workflow permissions, it rejects the external request and forwards the decision to the gateway. On the other hand, this routine accepts a request if it has the required data permissions for executing absolute function invocations in its trajectory through the workflow. It also creates a permissions table for conditional function invocations, which may or may not occur in this workflow. At this point, the request does not need to satisfy the permissions required by the conditional functions, thus offering a great deal of flexibility in designing security policies. The forward proxy then directs the request to the appropriate function container. When eventually a conditional function invocation actually takes place, like bar is getting invoked here, the conditional policy evaluation routine is invoked. This routine consults the lookup table to compute whether the request has the necessary permissions to execute function bar and then either accepts the request or denies it and forwards the decision to the internal request handler in the API gateway. In this example, we saw that William is able to proactively deny ingress requests based on insufficient permissions for future downstream function executions. Consequently, William is able to avoid partially failed execution of workflows and can improve performance by saving compute cycles. William is implemented on top of open source serverless framework OpenFaaS and is deployed on a Kubernetes cluster. It took about 400 lines of Go code to modify OpenFaaS to support William. William is evaluated using the popular proof of concept serverless retail application from Nordstrom, which consists of 12 functions. As William mediates activity at the workflow level, we now compare performance of William to vanilla OpenFaaS and Trapeze using three end-to-end Hello Retail workflows. William shows an average 0.51% execution overhead. This overhead is due to the searches required to determine if the request has the required permissions. In contrast, Trapeze imposes significant overheads on two of the three flows, specifically in conditions in which many data store read operations occur. To demonstrate the potential performance savings by proactive authorization mechanism in William, we measured the latency of 100 concurrent requests with increasing proportion of unauthorized or bad traffic being issued to the ingress point. Each bad request is correctly formatted but lacks the required permissions to execute downstream functions after the ingress point, potentially resulting in wasted computation. If Williams' proactive authorization mechanism is effective, we expect to see decreased latencies for William as compared to other systems. We observed that indeed William greatly outperforms all of the other systems as the proportion of bad requests increase. To conclude, I presented the design of a serverless access control framework, William, which was implemented and evaluated to demonstrate modest performance overheads. Our system code is open source and is available at the given link. Thank you for giving me this opportunity to present our research, and I am now open to take questions. Thanks.